Good morning, students. In previous lecture, we discussed about basic terms used in thermodynamics, and now we'll start with the main topic, internal energy and the first law of thermodynamics. Before discussing first law of thermodynamics and internal energy, I just want to let you know about the zeroth law of thermodynamics. Actually, it is a kind of definition of temperature, and it states that if two objects A and B are separately in thermal equilibrium with a third object C, as you can see in the figure, then A and B are in thermal equilibrium with each other. मीन्स ए और बी दो ऑब्जेक्ट्स अलग अलग एक थर्ड ऑब्जेक्ट के साथ अगर थर्मल इक्विलिब्रियम में है, देन दे विल automatically be in thermal equilibrium with each other. So this is the zeroth law of thermodynamics, which actually allows a definition of temperature. Next is internal energy. Internal energy is a very important thermodynamic property of a system, which is actually the total amount of energy stored within the particles of the system, or the energy associated with the particles of a system is said to be internal energy, and it is designated a symbol U, and it is calculated by or you can say it is the sum of different types of energies associated with the microscopic components of the system. Means system में जो मैटर है उसमें जितने भी पार्टिकल्स प्रेजेंट है, all different types of energies which is associated with those particles or other microscopic components are or is collectively called as internal energy. And these different type of energies include kinetic energy, potential energy, and different types of vibrational, rotational and translational energies related to the motion of the atoms and molecules, energy of electron, chemical bond energy. All these energies, when if we sum up all these different types, then we get the formula of internal energy, or you can say U is equal to different forms of energy: electronic energy plus nuclear energy plus chemical bond energy plus kinetic energy plus potential energy of atoms and molecules present in a system. Internal energy is an extensive property. As we have already discussed this term, extensive properties are the properties which depend on the amount of matter present in a system. So, internal energy, as it is dependent on the amount of matter or the quantity of matter, or you can say the size of the system, hence it is an extensive property, and it is a state function, because the change in internal energy when we move or when we carry out a thermodynamic process in which the internal energy of a system changes from U1 to U2, and this final state is obtained by following any path, then the change in internal energy is independent on the path followed to carry out it. So that is why it is a kind of state function. Internal energy of a system is a function of temperature, because as we increase temperature, the kinetic motion of the particles increase, that result in increasing internal energy of the system. And internal energy of a closed system can be changed by two ways: by supplying heat to the system or by doing work on the system. So in both of the cases, internal energy increases, and changes in internal energy result in changes in measurable properties of the system like temperature, pressure and volume. So this can be, you can say, observed by looking or observing the changes in these macroscopic properties of the system. So as you can see here, internal energy of a system, initially it is suppose U1, and Q amount of heat is transferred to the system, supplied to the system, and W amount of work is also done to the system. Then finally the new internal energy of the system is U2. Then it is observed experimentally that U2 is equal to U1 plus Q plus W. That means the total internal energy which is increased now after supplying heat and doing work on the system will be equivalent to the sum of all these different types of energies. So this is of first law of thermodynamics, that any type of energy or you can say energy can transform from one form to another form during a process. मीन्स जितनी हीट हमने सप्लाई की वो सिस्टम की इंटरनल एनर्जी राइज कर रहा है, जितना वर्क सिस्टम पे किया दैट रिजल्ट्स इन एन इंक्रीज इन इंटरनल एनर्जी ऑफ द सिस्टम. तो व्हाट वी कैन सी दैट दीज different energies can never be destroyed nor be created in a process. Rather, they keep on transforming their forms. So suppose and this change in internal energy for a particular process can be defined as delta U is equal to Q plus W, and this is the mathematical formulation of first law of thermodynamics. And here you can see this is a animated form, you can say, of first law of thermodynamics, where different forms of energy conversion can be seen. So that means energy can always transform from one form to another, but actually it remains constant in the universe. The entire energy content of the universe remains constant. We can define first law of thermodynamics as it is the law of conservation of energy, which states that energy can neither be created nor be destroyed, but can be transformed from one form to another. Or in other words, we can also say total energy of universe remains constant. जितनी सिस्टम अगर कहीं हीट सराउंडिंग से एब्जॉर्ब कर रहा है तो जितना एनर्जी चेंज सराउंडिंग्स में आएगा उतना ही इक्विवेलेंट एनर्जी चेंज सिस्टम इंक्रीज करेगा. तो ऑब्वियसली द टोटल अमाउंट ऑफ एनर्जी ऑफ द यूनिवर्स इंक्लूडिंग सिस्टम एंड सराउंडिंग्स विल बी कांस्टेंट. So this is a very important formulation of thermodynamics which relates internal energy changes of any system with heat and work. Now we can see that how these terms can be related to each other. If a system undergoes a change from an initial state to a final state, then we have already seen that change in internal energy is equal to amount of heat supplied plus work done on the system, where Q is the amount of heat. It may be either absorbed or evolved by the system, and W is the amount of work done on or by the system, and delta U is the change in internal energy. Now there are some important sign conventions which are to be very important to use while solving numericals on the basis of first law of thermodynamics. The sign for heat, if heat is supplied to the system, Q is given positive sign. Whenever system absorbs heat or it gains heat, so the sign for the heat Q will be given as positive. But if heat is released out by the system to the surroundings, or you can say heat is evolved by the system, then it is given negative sign. When work is done on the system, generally when a gaseous system is compressed by applying high pressure, then work is done on the system, and in this case the sign of W is given positive. And if work is done by the system, and this is generally taking place in case of gases, when gases expand against external pressure, then the work done by the system is given in negative sign. So these are the sign conventions given for work and heat energies. And changes in free energy, if the temperature increases, delta U will be positive, and if the temperature decreases, delta U will be negative, and delta U will be 0 if the temperature remains constant. First one example we can see. Calculate the work done by the system if 40 joule heat is supplied to it and the internal energy of the system increases by 32 joule. So in this question we need to find the work done by the system when 40 joule energy, heat energy, is supplied to the system. So value of we will apply first law of thermodynamics here. mathematical equation delta U is equal to Q plus W. Here Q is the amount of heat supplied, 40 joule, and it is supplied to the system, so value will be plus 40, positive in value, and internal energy of the system is increased by 32 joule. So obviously it will also be in positive. So let us write these values. 32 is equal to 40 plus W. The work done by the system is obtained as minus 8 joule. Here negative sign indicates that work is done by the system. Hence we can write the answer as 8 joule of work is done by the system in this process when 40 joule heat is supplied to it and internal energy is increased by 32 joule. As you all know that in simple physics, work is said to be done when a force is applied on an object and the object moves in the direction of force. In case of thermodynamics, generally we consider the mechanical or work which is actually a kind of pressure volume work. Here this pressure volume work is a kind of work in which gas expands or compress against external pressure, and this is also called pressure volume work. So gases can do work through expansion or compression against a constant external pressure. If this external pressure is higher than the internal gaseous pressure, then you can say gases are compressed and the work is done on the system. But if this external pressure is lesser than the internal pressure of the gas, then gases spontaneously expand, and this is called work is done by the system during this expansion or the increase in volume. So we can say in both of the cases, you can say a change in volume takes place against a constant pressure. So we can say that this is the pressure volume work of expansion or compression. And always remember, when a gas expands against a constant external pressure, then it is actually due to the decrease in internal energy of the system, and the sign, according to the sign convention, this work is done by the gas, hence it is said to be negative work. And secondly, when gases are compressed by applying pressure on the system, then the internal energy of the system is increased and work is done on the system and it has a positive sign. In both of the cases, the amount of work done by the system or on the gas can be calculated by this mathematical formula. W is equal to minus P delta V. As we have already discussed that in thermodynamics, work or any process in thermodynamics can be carried out in two different manners. If it is carried out very rapidly, or you can say it is difficult to reach or too difficult to reverse each and every step, and it is almost difficult to get equilibrium in between the process, then it is said to be irreversible process, and work done in such an irreversible expansion or compression of a gas can be given by this equation. W reversible is equal to minus P external delta V. Here this P external is the external pressure applied on the gas, and delta V is equivalent to change in volume. Means if the gas is expand or the expansion is taken place from initial volume V1 to V2. So in that case, work of expansion can be calculated by this formula. And suppose if the same expansion is carried out in a reversible manner. Reversible manner means by following infinitesimally small you can say steps, that after each step the system attains a kind of equilibrium. Then we can find the work done by this equation. Reversible work of expansion or compression is equal to minus 2.303 nRT log to the base 10 V2 over V1. Here this V2 and V1 are final and initial volume respectively. Now we'll relate internal energy changes with heat and work for various different processes. Let us see first for isobaric process. In an isobaric process, pressure remains constant. So for constant pressure, you know, as we have already done about the work done, how gases can expand or compress against external pressure constant. So delta U can be related with Q and W both. Delta U is equal to Q plus W, and if we write W is equal to minus P delta V, then we can also relate delta U is equal to Q minus P delta V. For isothermal process, temperature remains constant, hence internal energy change will be zero, as temperature or internal energy is directly dependent on the temperature. If there is no change in temperature, delta U will remain constant. And in such kind of system, jitni heat hum system ko supply karte hain, that is directly get converted into the work done by the system. Means utna hi system work kar lega, internal energy mein koi change nahi aayega. So for an isothermal process, Q is equal to minus W. Isochoric process have volume constant, and if volume, no change in volume is occurring over there, then according to thermodynamics, pressure volume work becomes zero, because delta V is zero, so W is zero. So in that case, the equation of first law will become delta U is equal to Q, and here this Q is actually supplied at constant volume, so it can also be denoted as QV. So we can say that for isochoric process, or you can say when heat is supplied to a system at constant volume, then it will directly result in increase in internal energy. So internal energy change is equal to heat supplied at constant volume. And lastly, adiabatic processes are those processes where system cannot exchange heat from the surroundings, or in this case Q will be equal to zero. Hence internal energy change is directly equal to the work done adiabatically by the system. That means if the system of the work is done on the system at constant heat, then it will increase in the internal energy of the system, and if system performs work itself, then it will result in equivalent decrease in internal energy of the system. Hence you can say delta U is equal to W adiabatically. So at last we'll discuss isothermal expansion of an ideal gas in vacuum. If a gas is allowed to expand in vacuum, and as you know that in vacuum pressure is considered to be as zero, because when it is vacuum, the no pressure will be there. So in this case, when external pressure is zero, the W, which is equal to P delta V, will also be zero. So in this case, no work is done by the gas during expansion if pressure is zero, or you can say if there is vacuum, and as the process is carried out isothermally at the same constant temperature, obviously delta U is also zero. So for an ideal gas, when it expands against a constant, or you can say against zero pressure in vacuum at constant temperature, then no work is done by the gas, no internal energy change is there, and no heat changes are there. That means W is zero, delta U is zero, and Q is also zero. So this kind of expansion of ideal gas against vacuum is also called free expansion of an ideal gas without consuming any type of energy. Hope all the things are clear to you all. Thank you and have a nice day.